Black holes, where time and space converge under the immutable force of gravity, are extremes of nature once deemed improbable. Yet now, they are beginning to yield their secrets. In fact, scientists have reached a point where they can envision what once seemed impossible, the black hole at the center of our own galaxy. We can now, in a sense, listen into the abyss. The concept of black holes was first proposed by German astronomer and physicist Karl Schwarzschild, barely a year after Albert Einstein published his field equations of gravitation in 1915. From the German trenches of the First World War, Schwarzschild wrote to Einstein, detailing the mathematical results arising from these gravitational equations. Tragically, this brilliant scientist later succumbed to a skin disease he contracted in the trenches, passing away at the age of 42. For 50 years, the existence of these so-called frozen stars was debated. Then, in 1967, physicist John Wheeler coined the term black hole to describe these objects and the conditions that would form them. New Zealander Roy Kerr advanced the concept by providing a solution to the equations which required black holes to spin like all other astronomical bodies. Later, Stephen Hawking and Roger Penrose theorized that black holes could emit what we now call Hawking radiation. According to this theory, if a black hole ceases to absorb material and grow, it could eventually evaporate, effectively shrinking and dying. The task for scientists, then, was to find one to study. Quasars, those incredibly bright distant objects, were considered a strong case for black hole accretion, as they appeared to be powered by the only imaginable energy source capable of such intense luminosity. In 1964, astronomers discovered one of the brightest X-ray sources in the sky, located in the constellation Cygnus, and named it Cygnus X1. This powerful source did not match any bright optical or radio counterpart, leaving it a mystery. Soon, with better computers and space-based telescopes like Hubble, black holes were eventually detected, or rather their effects on their surroundings were identified. By their very nature, black holes themselves cannot be seen. Black holes are incredibly fascinating but also deeply mysterious. We know they sit at the centers of galaxies, influencing how those galaxies grow and ultimately fade. They swallow up gas and stars, acting as enigmatic objects that exist at the intersection of our two great pillars of physics, general relativity, which describes gravity, and quantum mechanics, which deals with the smallest building blocks of reality. Black holes are literally gravity unbound, purely gravitational objects predicted by Einstein's general relativity. Their most notable and terrifying feature is that once something enters, it never returns. The word that comes to mind first is wonder. Such objects were never truly expected to exist in nature until quite recently. In fact, I remained a skeptic about black holes as recently as 20 years ago. Black holes are places where Einstein's theory of general relativity is the complete story, not just a mere perturbation layered over Newtonian theory, which adequately explains the dynamics of planets in our solar system. As a result, black holes offer a unique environment to probe general relativity specifically, and the realm of strong gravity in general, with implications that span the cosmos. I find that particularly interesting. This one piece will produce 52 layers, watch on mobile devices or a big screen, all for free, no subscription required. If you want to test the fundamental theories of the universe, you go to its most extreme laboratories, and a black hole is precisely that. Seeing a black hole not only confirms their existence, it also lets us test some of the fundamental predictions of Einstein's theory of general relativity, the theory that fully describes space and time. Such a level of testing has never before been possible. If you're fascinated by unadulterated gravity, black holes are one of the most intriguing examples. My role in this project is that of a theorist. I work with equations and simulations, trying to determine whether the images we produce match the predictions of Einstein's theory, or if they suggest something else. From a physics standpoint, I find it intriguing that this may be some kind of rent or tear in spacetime, a place where our understanding falters and where serious questions arise about information theory. I was incredibly excited the first time I saw the initial image. For so long, this was only theoretical. We predicted certain features, but we couldn't be sure. Now we know. In that moment, all our uncertainty collapsed. As magnetized gas falls into a black hole, it heats up and generates the light we eventually detect. From our everyday experience, we expect light to travel in straight lines. But here the situation is very different. The black hole's intense gravity bends and deflects light rays away from the straightforward paths we take for granted. In fact, the bending can be so extreme that we can see objects behind the black hole, objects we would expect to be hidden, simply because the light is curved into our line of sight. Scientists began running simulations on supercomputers, creating multiple computational models to better understand what we might find in the observational data. After computing the radiative signatures of these simulations, we compare them to observations. Imagine you're in a stadium during a football match and have an image. You want to see if this image matches one of the 60,000 spectators. To do this, you rotate, scale, and adjust contrast to identify what's in your picture, whether it's a person, a cat, or something else, and then try to find it among all those spectators. This is far from trivial. It's computationally demanding, requiring a supercomputer. We developed a genetic algorithm that smartly navigates through images, adjusting them for a match. The entire process can take about a month, and afterward, we might find around 10 spectators who fit the image. This is very similar to how we match observations with theoretical predictions in the EHT. The most surprising aspect of this experience is that we succeeded in obtaining a very good image on our first synchronized attempt when we aligned all these telescopes simultaneously. It's not surprising that the image aligns with our simulated predictions because we trust our simulations and Einstein's theory of general relativity. In 2019, the team achieved a monumental result, an image of the shadow of a massive black hole in the distant M87 galaxy. This was a world first, celebrated across the globe. I think we've been extremely lucky. I expected we'd have to work for years, conducting many observations before achieving a final image. Yet when we observed our first source, we immediately saw that ring, that event horizon, that dark region. We knew instantly that we were looking at an event horizon, a black hole viewed simultaneously from all sides, a region where time effectively stops. It's a completely different part of the universe we're seeing for the first time. If we want an image of a black hole, the main problem is that they are very small. So, we pick a very large black hole, which is unfortunately very far away, requiring an enormous telescope. Our telescope is 100 meters in diameter, but still not enough. We need something even bigger, but we can't build it physically. Instead, we create a virtual telescope as large as the Earth itself by linking multiple telescopes scattered around the globe, even one at the South Pole. With this, we achieve remarkable image sharpness, comparable to seeing an orange on the moon. Black holes suggest that there are regions inside them we cannot explore. For a physicist, that is both unsettling and appealing. We dislike facing doors we cannot open. Inside black holes, we expect physics to break down completely, adding even more fascination. The future of the project lies in furthering fundamental physics. If black holes are the extreme objects where we can study gravity, and if general relativity breaks down at the event horizon, then perhaps new data will help us examine the physics beyond general relativity. Maybe quantum physics rules beyond the event horizon, or some combination of quantum physics and general relativity, quantum gravity, currently non-existent as a complete theory. But by studying black holes, we may learn more. Our experiments are like Arctic expeditions. We plan for months, gather equipment, and then people migrate to observatories worldwide. We stay up all night operating telescopes. Then comes the waiting, hoping it all worked. We combine all our data and only then know if we succeeded. After that, the hardest part begins, analyzing the data thoroughly to ensure accuracy. Data analysis, imaging black holes, and conducting simulations is thrilling yet challenging. It requires patience and a long, careful process. But seeing the final product is incredibly rewarding. The Event Horizon Telescope, EHT collaboration, is a remarkable group of experts from around the globe, Americans, Europeans, Asians, united in their technical and scientific expertise to produce an image of a ring around a black hole. The project's future is exciting. Now that we've seen what we're after, countless new questions emerge. Can we determine if Einstein was correct? Can we understand how gas falls into a black hole or witness huge blasts of radiation and particles? There's so much more to do. We've only just begun. Next, we want to make the first movie of a black hole and understand how space-time rotates around it. We'll accomplish this by adding more telescopes worldwide, sharpening our virtual lens. This collaborative success combined talents from many people, enabling a feat otherwise impossible. To capture this image, multiple radio telescopes had to work simultaneously around the planet. With new goals in mind, the EHT decided to target the black hole in Sagittarius A, the center of our own Milky Way galaxy. It's much closer but also smaller, veiled by gas and dust. Normally, looking into a galaxy's center is blocked by dust, but radio waves pass through obstacles. By combining a telescope like this one with others worldwide, we can peer into the galaxy's heart and see its black hole. The scientific result is only one milestone in a long timeline. We are constantly learning how the instrument works, how teams collaborate, and how new theories arise. It's an evolution, never a single endpoint. Mysteries remain, problems await solutions, and many questions about black holes persist. The Event Horizon Telescope set its sights on Sagittarius A, our galaxy's own central black hole. The long-term future may involve moving such instruments into space, enabling even sharper images by achieving higher angular resolution. In 20 or 30 years, we might create detailed images of a black hole's event horizon. Not only did scientists image the black hole, they also sampled radio emissions from the surrounding hot gases, giving us an auditory representation, the sound of a black hole. So far, we've focused on the nearest massive black hole, but quasars are much farther away. With gravity, we can observe gas motions and measure masses precisely. By studying many quasars, we might solve how massive black holes influenced galaxy evolution. Since essentially every galaxy has a massive black hole at its center, understanding their relationship is crucial for grasping the universe's evolutionary history. By analyzing data from the EHT, researchers continue unveiling more details. X-ray emissions reveal magnetic field lines through the orbiting gas clouds. Further exploration of these X-ray emissions is ongoing with a new space-based X-ray observatory, the Imaging X-ray Polarimetry Explorer, or IXPE, launched in 2021. IXPE studies extreme cosmic objects, pulsars, neutron stars, black holes, through polarized X-ray radiation, revealing more about these high-temperature environments around black holes. Beyond that, black holes' extreme conditions let us study neutrinos, the most abundant particles in the universe, which rarely interact with matter. They seem to be produced by extreme events like exploding stars and fast particle jets from supermassive black holes. Merging black holes produce gravitational waves that ripple through space-time, detectable here on Earth. Another observed event was the flipping of a magnetic field around a massive black hole, temporarily brightening surrounding material, reducing X-ray emissions, and making the X-ray corona vanish until the flipped field regained strength. We've also seen a black hole devouring a star that ventured too close. Its ejected super-fast jets of material interacted with nearby dust clouds, aiding in planet formation. These singularities seem woven into the cosmic tapestry of destruction and creation, influencing stars and planets. While we don't have all the answers, discoveries like these guide us toward deeper understanding. For millennia, we have gazed at the stars and galaxies in awe, wondering about our place in the cosmos. Current technologies let us see further and farther back in time, with more detail than ever. The next generation of orbiting telescopes will soon begin service. Who knows what giant leaps they will enable in our understanding of the universe? I want to stay here. Since its launch in 2013, ESA's Gaia Observatory has continuously mapped our galaxy, creating the most detailed and complete multidimensional map of the Milky Way. Its latest dataset includes even more improved information on nearly 2 billion stars, solar system objects, and extragalactic sources. Our Sun travels at 240 kilometers per second around the galactic center, taking 220 million years to complete one orbit. Gaia's data includes stellar positions, distances, and motions across the sky, plus color information and, crucially, radial velocities for 33 million stars in the Milky Way. This allows astronomers to craft the most accurate and complete multi-dimensional map of our cosmic neighborhood. Another novelty in this data release is the largest catalog yet of binary stars in the Milky Way, vital for understanding stellar evolution. At the Observatoire de Paris in Meudon, France, scientists are part of the Data Processing and Analysis Consortium, a 400-person team from 20 countries that processes Gaia's data to produce the Gaia catalog. Gaia is extremely important for all aspects of astronomy. Its catalogs contain immense amounts of data, providing a foundation for astronomers worldwide for many years to come. With each new release, the number of observed stars, solar system objects, and extragalactic targets grows, and more details are added, forging the most detailed overview of our galaxy. Gaia is an incredible satellite that observes 1.8 billion stars. It studies everything from nearby asteroids to distant quasars. For these 1.8 billion stars, Gaia can determine distances and astrophysical parameters, essentially giving each star an ID. Until now, Gaia provided a lot of positional and motion data, but now it also offers astrophysical characteristics for nearly all these stars, including variable stars, classification, and more. This time we provide new measurements such as stellar brightness in various bands, rotational velocities, atmospheric parameters, chemical compositions, and interstellar material abundances. Gaia observes with three main instruments. One measures position, astrometry, another measures brightness and color, photometry, and the third is a spectrograph that provides radial velocities and reveals atmospheric details. By examining a star's spectrum, we can determine its speed relative to us. Even older than Gaia is the venerable Hubble Space Telescope, which continues contributing to cosmological science. Perhaps Hubble's most important discovery is dark energy. Among countless discoveries, the realization that the universe's expansion is accelerating is particularly extraordinary. Instead of slowing under gravity, it's speeding up, which earned a Nobel Prize. Without Hubble, confirming this would have been nearly impossible. We now call that mysterious force dark energy. Is it simple or complex? Could there be multiple kinds of dark energy? Hubble refines the expansion rate measurements, comparing observed data with predicted values. We're seeing discrepancies that open new mysteries. Astronomers are also puzzled by dark matter, how it behaves and where it concentrates. Observations show small, dense clumps of dark matter bending and magnifying light more than expected. Dark matter dominates galaxies, holding them together in massive clusters. This mass warps and magnifies light from distant background objects, a phenomenon known as gravitational lensing. By studying how background galaxies' light is distorted, we can map dark matter's distribution. Strangely, in some galaxy clusters, the concentrations of dark matter create lensing effects about 10 times stronger than predicted. The upcoming ESA mission, Euclid, aims to probe dark matter, dark energy, and the expanding universe in even greater detail. Euclid will image billions of galaxies out to 10 billion light-years, improving our understanding of cosmic expansion and structure growth. It's a cosmology mission scanning the sky with unprecedented accuracy, allowing a clearer picture of the universe's history and expansion. Euclid features a 3-mirror anastigmat design, with a 1.2-meter primary mirror to cover visible and near-infrared wavelengths simultaneously. The mating of Euclid's payload module with its service module marks a significant step, merging two components developed and tested separately. A large international team has worked together for years to achieve this milestone. After integration, Euclid will undergo a 6-year mission, possibly extended by 5 more years to gather data before launch. After the mating, the next steps include integrating the solar arrays, sun shield, and the high-gain antenna. Environmental tests will follow, culminating in launch. Around the same time, NASA's SPHEREX mission will survey hundreds of millions of galaxies, including the earliest ones, and search for water and organic molecules in the Milky Way. SPHEREX will map the entire sky in nearly 100 near-infrared colors, providing a new perspective on cosmic history. We believe that in the universe's earliest fraction of a second, it underwent rapid inflation. Spherex will map galaxies in 3 dimensions over the whole sky, probing how matter is distributed and how galaxies formed and evolved. It will also identify targets for deeper study by NASA's James Webb Space Telescope and the future Nancy Grace Roman Space Telescope. The Nancy Grace Roman Space Telescope, launching atop a SpaceX Falcon Heavy, will combine Hubble's resolution with 30 years of technological advancement and a field 100 times larger. By observing in certain infrared wavelengths, Roman will peer through dust and reveal hidden stars and galaxy growth over the last 10 billion years. Accurate distance measurement is crucial, and astronomers rely on standard candles like Type Ia supernovae to gauge cosmic scales. Roman will also search for exoplanets within our galaxy using a coronagraph that blocks a star's light, letting planet-reflected light through. Deformable mirrors with hundreds of tiny pistons will remove distortions, improving image contrast. This technology allows us to see objects more than 1 billion times fainter than their host stars, potentially showing planets in star systems similar to ours. The Nancy Grace Roman Space Telescope will also look for clues of dark matter and dark energy in the distant universe, offering an unprecedented combination of breadth and depth. This will usher in a new era of observing and understanding our cosmos. Wow!